All right. Next thing to talk about in terms of Bayesian data analysis is the idea of regression. So at long last, we've kind of arrived at one of the areas where Bayesian analysis really shines, and it gives us a clear logical framework for dealing with cases where a lot of frequentist statistics kind of break down. Before I get going, I want to call your attention to a couple resources that I found really helpful in preparing these notes. So I've cited this Sibia book before, Data Analysis, a Bayesian Tutorial. But I'd also like to call your attention to this article by David Hogg et al. It was posted on Archive called Data Analysis Recipes, Fitting a Model to Data. These are both good frameworks for kind of thinking about things and taking your ideas of regression to the next level. So to get started, let's use the past as a way of setting the stage. Now, we teach linear regression in first year physics. We teach it again in lab courses. All of these things are nominally really easy. We put in the idea that we have a variable, y, and it is described in a model of a linear slope. So mx plus b. And then we assume that every ith datum in our model is some nominal slope times the x date for that datum plus b plus some random deviate epsilon, and that epsilon is determined from a normal distribution with mean of 0 and some known variance y sub I for each point. Now, this has a lot of assumptions, and we usually rattle them off and then pay no further attention to them. So we assume that the xi are perfectly known. There are no uncertainties in the x coordinate. We assume that the variances are known. We assume that the line is a complete description for the data. So that means that the yi are absolutely determined from just the linear relationship between mx plus b plus a little bit of noise with known properties. And you are asking the question, how does y depend on x? So x is your control variable and y is your response variable. And if all of these things are true, linear regression is exactly what you want to do. But one of these assumptions is often wrong, and that just voids the warranty on the analysis that we're doing in regression. And that's normally okay because you get a reasonably looking fit, but your ability to do things like interpret the probability of correlation, for an example, like the R coefficients for these, those don't necessarily turn into the probabilities that the frequentists tables will tell you are actually true. And this is where it becomes a little bit more useful to cast this into a Bayesian framework. The Bayesian framework looks a lot like linear regression. We sort of view this same problem as we say, we're going to determine the y data is conditioned on the x data, the known variance, the slope, and the intercept, and that just follows this Gaussian distribution. It's the same place we derive the maximum likelihood estimator under linear least squares from is exactly this. So it just follows the Gaussian distribution, and you have this loss term, this goodness of fit term, which is just yi minus the function of x quantity squared, gives us this value. So this is the likelihood of drawing our data from a line with those parameters. And then using Bayes' theorem, we can determine what the slope and the intercept are as the set of data, as conditioned on the set of the data and the background information. And because we're in linear least squares, where our xi and our sigma I are perfectly known, those just become part of our background information. So they're just kind of coming along on the ride. And then we get our likelihood expression here. We get our priors on the slope and the intercept. and then we get the probability of drawing the data from the background. So we set priors on M and B, but this largely follows everything we've seen before on maximum likelihood estimation. So let's do this. It's straightforward. Here's some data. These are the data drawn. These are the example data in the Hogg article. I believe there's some sort of galactic properties. Doesn't really matter what they are, but it's an X and a Y relationship. And we want to determine how Y depends on X. I think we're fancy because the errors have different sizes. So we have to do some weighted least squares. We calculate all that. We identify the maximum of chi-squared space. And then we find that there is a relationship between Y and X with these parameters shown here. Maybe a little over precise in my intercept, but be that as it may, we get a resulting line that goes through the data here. Everything is great. So what we get out of this is we actually are using these in the context of the posterior probability density on M and B. And these quick numbers that fell out of the stats models package in Python for me were just telling me a bit about the probability space of M and B. And so I'd set up some prior range on the slope, which was sort of 0 to 5, and then the intercept, which was running from -50 to 100. And I was able to just evaluate the posterior probability on that grid. And this gives us our full set of priors. Maybe I've shown here. And so what you see here is the contours of the log probability at the intervals of 1/2, 4.5, and let's see here, 1/2, 2, and 4.5, showing me my different 1, 2, and 3 sigma cuts around my maximum value here, which is indeed the 2.2 and 30 that are present on the best fitting values over here. So the 2.2 and the 30 is just the local maximum right here. Now what we can do is we can take this parameter space and we can marginalize it, just collapse it over the two different axes. And when we do that, we just add that up and we get the posterior for our parameters for the intercept and the slope. And the maximum likelihood estimator is right here in the center because this is a glorious and nice unimodal posterior with a Gaussian distribution. The widths here correspond directly to the fits. Everything is making us feel good about this regression. So then we start to ask, well, that was all nice. What happens when your data gets worse? Here are the same data, but I have thrown in 4 bad data. 1, 2, 3, and 4. Those 4 data don't look like they belong to the line that I care about, but if I just blindly go in and start doing some regression on them, out comes a line. Well, this is great. So you get 1.1 plus minus 0.3, and then some different intercept value here. So it's showing up. You get a nice shallow line because, this one's got super small error bars, and it pulls the line over like that. We definitely are reporting the data, and if we are blindly just going ahead and saying this is the value and these are the results, this is a good representation of what the maximum likelihood estimator is, but this immediately looks like it starts to void the warranty on linear least squares. This does not look like a case where the data are drawn from the line that's shown here with a, that are only distributed around a single line with the uncertainties. This point here is something like 10 sigma from the value here. You wouldn't expect that under a normal regression. You would expect at most a couple things that are 2 sigma or more away from the data points. So there's a problem implicit in this analysis. And so this line is going to be garbage because we have voided the warranty on least squares. goes through the data, I guess that's something for it, but that's about where we can do. So what can we do? Well, in a frequentist framework, maybe you would just go through and you'd start to trim some results. That one, get rid of that one, get rid of that one, get rid of that one. I don't know. Maybe keep this one. Don't know about that one up there. You would have to come up with some iterative application of rejection criteria. Something would go on. But with the Bayesian framework, we actually have a nice way of dealing with it, which is just to say our data has some bad data in it. And what we see is a mixture of good data and bad data. So what we're going to do is we're going to model this as two different data distributions. We have some bad data, some fraction of those data, bad data. And they're drawn from a distribution with some mean y value and very large variance. We'll call that VB and YB respectively. And then what we want to do is we basically want to say that every datum comes along with it and has an indicator variable. And if it's part of the good data set, we'll give that indicator variable a 1. And if it's part of the bad data set, we'll give that indicator variable a 0. And then we can figure out what the probability is, the likelihood of drawing a data set yi from the line is basically some, the slope, the intercept, whether it's part of the good data or the bad data, the y-intercept or the y-offset for the bad data population, the variance of the bad data population, and then everything about the x's and the sigmas that's in our background information. And so when we sort of work all that out, that's the product of basically belonging to the good probability density distribution function and then the bad probability distribution function. And you notice that the indicator variables here, if it's good, this term here is going to be 1 and you get the good probability. And if it's 0, this term here is some number to the 0 power, so that's just 1. And then this bad variable becomes 1 minus 0 and it turns on. So this indicator variable is a nice way of just indicating whether it's good or bad. And then mathematically just using it as the exponent in this product allows us to figure out whether it belongs to the good data or the bad data. So we go ahead and say that, all right, the good data, it's just the regular Gaussian probability distribution function model for our resulting fit. So that's, got the line width and then the slope, chi-squared like term, everything is great. The bad probability model only depends on the y sub b, the variance, and the background information. And so that's 1 over, and we're going to include the square root of 2 pi times the variance plus the uncertainty in the data squared. And then that's going to be e to the minus offset from the y offset squared, and then 2 times the variance plus the variance from the observations in the denominator. So what that means is that this is basically just a big Gaussian band in the y direction, and the data are drawn somewhere from that. And the variance can be huge. It can be like 50,000 or something like that. And that would basically be flat, but it would then start to tail over at the far end. So this gives us a model. It's good data or bad data. And our bad data model will largely do a good job of representing highly scattered results out here. Okay, so if that's our model, then what we can do is take some prior probability on the indicator variables, qi, and that comes from the binomial distribution for some probability of being bad. So we're going to give this hyperparameter p sub b, it's basically the probability of being bad for a given data and a given datum, and then the PDF for those indicator variable, that set of indicator variables is just going to be the product of the, basically going to be a Bernoulli distribution, which is basically the probability of being bad to the qi, probability of being bad to the 1 minus qi. So that's basically the heads or tails kind of distribution function, for PB being the probability of coming up heads, in this model. I guess coming up tails as we've written it down. But we saw this a lot earlier in the lecture series of this kind of probability density function. So now we're done. We have a complete model in terms of all these parameters, which are basically, it's a huge space. We got the slope, the intercept, an indicator variable for every one of the data, the probability of something being bad, the variance of the bad data, and the y offset of the data set. And then we just have some Bayes theorem application to determine the posterior probability of the parameters is the likelihood of the data times the priors that we have been very careful about writing down, divided by the divided by the evidence term. That looks like a mess, but I don't care whether a given datum is good or bad. I only want a slope and an intercept. Why won't you let me have just a slope and an intercept? That's the problem. And the solution here is just to engage in parameter marginalization. So that's what we're going to do. We are going to take this extensive PDF and start to marginalize out. We will, for compactness, drop the evidence term and focus on the posterior for the slope and the intercept, given the data and all this background information, is going to be the integral over all of these nuisance variables, all the possible permutations of the QIs as ones or zeros. So that'll basically give us, they can only be in these two different states. So it's sort of a sum over these two different states, times the integral over the probability of the different probabilities of being bad. Seems like it should range from 0 to 1, range of the variances, range of the bad data. Now, the way we framed this with the Bernoulli distribution means that when we integrate over all of these DQI and these probabilities, we essentially end up with every point has some probability of being good or being bad. So if we condition on a single datum in our measurement set and we carry out the integral, some of the times the indicator variable is good, some of the times the indicator variable is bad, but then that's multiplied by the likelihood of that point being drawn from the two different distributions. And we end up with this mixture model of this that sort of describes this marginalization process, which says that the probability of a slope is proportional to the product over all the different data. And basically a given datum has some probability 1 minus PB of being in the good data set, and then PB of being in the bad data set. So it essentially, and that PB is the same for all of the data sets. So if it's near the good data set, it's going to, the locus of high probability for the good data set, this term is going to contribute a lot to the probability. But if it's sort of way off in the bad corner of parameter space, then it's going to come and this term is going to contribute to the probability. And what this does, if you sort of think about this in kind of a chi-squared space, is that there's a little valley in chi-squared space with weight 1 minus PB, that if the data are in that valley, they contribute heavily to the probability. But if they're off, and they belong to this bad part of the probability distribution, it kind of acts as a maximum value. And so while it's unlikely to be drawn from the good data set, this bad probability, this bad data PDF is there to say it's okay to the datum. You belong to this. So it gives us this essentially this, the value and probability density space, but then it gives us kind of a maximum penalty that a individual datum can accept. And it doesn't, if it's way off from the line, it doesn't contribute quadratically to the, basically to the fit there. It essentially says, oh, this is likely a bad data, stop counting, it's likely in that distribution. That's all that's there. So this mixture model allows us to kind of say, if you're far away from the locus of best fit, you just belong to the bad data distribution. You don't contribute and penalize the good fit. You're just part of the bad data. Okay, so with that as preface, we can assume some priors. I set a tight prior on the slope and the intercept. I assumed that the probability of being bad was somewhere between 0 and 1. And then I distributed the log of the variance, so as a Jeffreys prior, on 3 to 10. Now, for purposes of getting something done without the full toolkit that we want to deploy here, I had to assume that the mean of the bad data was equal to the mean of the observed data. And what that does is it reduces the dimensionality of the problem. Right now, our priors are 4-dimensional, and if I add another one, it becomes 5-dimensional. And that was about as much as my computer could handle, was the 4 dimensions, and doing 100 samples along those. That ends up as 100 times to the 4th power is 10 to the 8 calculations, and that didn't take forever. Adding another 100 would have required 10 to the 10 different probability calculations to sample this probability grid, and that would have been extensive. So I solved this by basically tabulating every probability on this 4-dimensional grid, and in doing so, I get a space that looks like this. Now, this isn't a 4-dimensional space. What this is the full probability, and then I've integrated along the PB and the VB axes to show you the posteriors for the slope and the intercept. And I get a value that's kind of 2.2 and 30, much like I did before. So it's all concentrated right there. And then we get this sort of large haze around. This is no longer a nice, tight Gaussian. It's starting to have a little bit of structure, but still unimodal, nice and well behaved here. So if I marginalize over all of the distributions, I get the posteriors for the slope and the intercept. The red lines here indicate the maximum likelihood estimates for the good data only that I calculated before I added in those 4 data. So that was the 2.2 and the 34 that came up from the previous analysis. That gave us this, and you'll see we actually get really close. Those are well within the credible ranges of our derived parameters here, even though we added in these 4 bad data. So this is really a successful approach. The probability of being bad has this structure here. This is essentially the fraction of bad data that are in the sample. There were 20 data total. 4 of them were bad. So we get a peak. It's a little larger than 0.2, but it's kind of there. And then the log of the variance here is peaking at around 8. So that's the variance is e to the 8. And so the sort of sigma equivalent would be e to the 4th. And so that gives me kind of the width of the bad data is about, I guess, about 100, a little under 100 in terms of its sort of sigma width, which if you go back and you look at the bad data distribution is about, sure, maybe 100 is a reasonable width here. So we did a pretty good job by just including some bad data. Few warnings though. This really works because we've got a good estimate on our uncertainties. Once we start developing this sophisticated model for the data, we really have to trust the information that we're putting into the model. And so I repeated this process, but I took all of the reported uncertainties and then I divided them in 2. So I assumed that the data were more precise than they were. And then my probability function doesn't look quite so nice. You start to get into this multimodal posterior where it's trying to lock onto a couple different slopes and is deciding, well, are these subsets of the data equal? Are these the good data, or is it this subset of the data that's the good data? And when you do that, you start to get a bit of a mess. If I do the full marginalization here, you'll see that I have multiple values for slope, and the probability differences between these two different values aren't that big. Like it's, only a factor of a few between them. It's not strongly preferred the way a nice Gaussian core model would be. So there's a fair bit of structure in these results. We have a much larger fraction of bad data, and that's because the good data variances can't explain the relationship to the fitting line. So we're getting something like 60 or 70% of the data are there. And so it's just choosing which 60 or 70% of the data we're throwing away to draw a line through it. So that's a caution here. This method is powerful, but you have to believe the uncertainties in your data. What if you don't? What if you assume that there's some data, but you actually think that there's probably a little bit of scatter in your relationship intrinsically? So your observed errors aren't the sole source of scatter around the line. We can model that. We incorporate this idea of introducing an extra variance term. And this just happens if you have a stochastic relationship you're trying to describe, say in a physics lab, and then you have uncertainties on top of that. Your uncertainties are measuring something that's going to vary around your relationship randomly. And in doing that, that extra stochasticity isn't represented in your uncertainties, but it does need to go into your data model. And if you do that, we just add some additional variance here. So all we do to incorporate this is we say, okay, well, stick on a little bit more variance into your data set. Give it a parameter v, and then you get a product of a regular Gaussian here. I've dropped out of the mixture model, and I'm just kind of including that in. I've gone back to my original data here, and so I can just include this extra variance term. And then we have a, just regular Gaussian, except we just pick up this extra scatter term. And you'll notice that the action of this is that if this variance gets too large, what's going to happen is it'll pull down the probability for the whole model. So on average, this whole thing favors a case with small intrinsic variance where possible, and it kind of has the push and pull of these two terms to determine whether the data set explains the variance well. Okay, we can set down a couple priors on the variance. The easiest one to calculate, and the one that I used, was just the Jeffreys prior, where we assumed that the log of the variance is somewhere, on a range v min to v max. Last time, or a few lectures back, we saw that a good choice here would actually be a conjugate prior on the variance. So you would just pick an inverse gamma distribution for the variance, and you could then tabulate that. But because we don't have quite our full toolkit, the Jeffreys prior worked out pretty well. And what I did is I went back and I used the data with their errors divided by 2, but then I did this sort of full tabulation with this extra variance term, and get these marginalized posteriors. Again, the red lines indicate the values with the correct errors and the maximum likelihood. And here we get a good estimate for the intercept and the slope respectively. And then I get a value for the log of the variance here. So that's what, 6-ish. And so that's e to the 3, or about 30, which is about the characteristic error bar size for our original data set. So, plus or minus 30 would be a good average error to add onto this to get this back to the right relationship. So we can actually infer whether there is scatter in the data. Now, I've done a mixture model and I've done an excess variance model. I'll just note that this whole system is modular. You can do excess variance plus a mixture model. Go ahead, toss that in there. It'll work just fine. It just increases the dimensionality of your parameter space, and that means you would just have to do more calculations to get these constrained fitting parameters. Okay, so it's a neat little toolkit. We can use the Bayesian framework, describe all our models, marginalize out, and get good conditional posteriors for our parameters. Very reasonable. So now let's turn to the hardest problem in statistics, which is linear regression with uncertainties in both axes. And this is often called the errors in variables method, or error in variables method. And I'm being facetious a little bit in that it's the hardest problem in statistics, but there is a wealth of methodologies that are applied in this case, and many of them are correct under the specific circumstances for which they are applied. We want to use this kind of way of Bayesian thinking to kind of give us some guidance through, see one possible way we could solve our approach, and then use that as a kind of platform on which we can think about the rest of this kind of analysis. So let's consider a data set here, which consists of the x's and y values this is the same data set I used previously with its associated 1 sigma errors. But I'm also going to introduce uncertainties in the x coordinate and covariances between them expressed as a correlation coefficient. And from this, we have several data coming down here. We're going to incorporate and develop a covariance matrix. So that's the x's and y's appear, the errors in x's and y appear on the diagonal, and then the off-diagonal terms is the correlation coefficient times the sigma x times the sigma y. And so that's how we will define a variance matrix for those data. And when we do that, we can plot each datum with an associated error ellipse. If you're trying to draw an error ellipse, what we do is we take that correlation or that covariance matrix that we just described, and we diagonalize it. So if you compute eigenvalues and eigenvectors, the eigenvalue or the width of that is the square root of the largest eigenvalue. That gives you the major axis of the error ellipse. The minor axis is the square root of the small eigenvalue, and so that gives us the width. So this is the major, this is the minor. And then we figure out its orientation with respect to the x-axis as the arctangent of the large eigenvectors y component over the large eigenvectors x component. So it's basically what's the orientation of the major axis of the ellipse with respect to the x-axis. The arctangent will get that out, and then use those as the angles and the sizes, and you can draw little error ellipses around all of your points, and then use that to try to find your resulting datum. So let's consider one possible way of describing this data model here. Let's consider a single point shown here. And what you see here is kind of the 1, 2, and 3 sigma probability distribution functions. So what we're saying is that this point here lies somewhere in a Gaussian centered on its maximum, and it has sort of declining contours of confidence. So it's very likely to be inside that ellipse and not very likely to be outside of this ellipse. And we want to then consider a trial fit to that line. So let's consider some random line y equals mx plus b going up here and slicing through this probability cloud. So this a two-dimensional Gaussian, and then we're going to consider a line that's running through that. And there's going to be some perpendicular distance that's going to be sort of the minimum distance of the point from the line, the observed point from the line. And what we want to do is we want to essentially figure out the probability that this point could be anywhere along this line. So it, as drawn, it's a little more likely to be here than here. But we can express this in terms of this offset geometry, this delta I. And what we want to do is take advantage of the fact that any slice through a two-dimensional Gaussian distribution is a one-dimensional Gaussian distribution. And we can look at this error ellipse as a projection onto that line. You can also think of it as an intersection between two Gaussians, one of which is infinitely thin and long, that's the line, and you're trying to calculate the overlap integral between those two Gaussians, one of which is infinitesimally thin. And there's well-established geometry for that, and we will express that in terms of a vector v here that is going to be perpendicular to the line model y equals mx plus b. So if that line has a slope of m, it's that angle is going to be the angle of that line with respect to the x-axis is the arctangent of the slope, and then the vector perpendicular to cos theta in the x direction and sine theta in the y direction is going to be minus sine theta in the x direction and cos theta in the y direction. So those two, that will be perpendicular for all angles theta to the line. And so we can actually measure what that offset is and then figure out the displacement of that closest point of closest approach in terms of this angle, the actual datum, and then the offset term correcting for the y offset of the whole line to figure out how far a point is from the line there. The variance when you project this along the line is going to be sigma I is just going to be the transform of the variance. This takes into account how that variance then rotates into the new frame, and when we take a slice along it, and that gives us a scalar variance that is just the projection of this variance with this unit vector. So we do this quadratic form contraction and get a scalar variance representing the sort of width of the line, and then that's taking into account basically where that point is at all points on the line. And then using the fact that it's a one-dimensional Gaussian, you can describe the probability of drawing the points y and x from this theta and b perp, which is the b cos theta term that I was using earlier, is just a Gaussian probability distribution function with the delta term taking the place as the offset, and then the sigma I is the new variance term. So we can then set a prior on the angle of the possible lines and some range of the perpendicular offsets, b min and b max, and this gives us a nice probability density function that we can sort of tabulate, integrate up, and identify. I'll just show briefly. This is kind of what it looks like. We get a very narrow possible range here for the angle and a offset here. So once we incorporate these uncertainties, we get a different offset, though the angle, this is in radians, gives us a slope that's fairly similar to what we have seen before. I want to come back and note one thing, that once we introduce this error in variables formalism here, we are considering the angle to be uniform on minus pi over 2 to, or minus pi to pi. So basically it can be infinitely sloped downward to infinitely sloped upwards, or somewhere in there. And by choosing a uniform prior in angle, what we do is we actually allow it to kind of sample all possible angles uniformly. And in an error in variables formalism, that kind of makes sense, because the normal prior, you would say, okay, the slope is somewhere between, say, 0 and 10 or something like that. That puts a lot of slopes at relatively large angles with respect to the x-axis, and that may be appropriate for your data model, but the uniform prior on the slope really concentrates that prior up at angles that are close to the y-axis, because most of, on any interval, most of the lines will be steep because of this inverse arctangent relationship between the slope and the angle. By choosing the angle to be uniform, you essentially are less biased towards any particular range of slopes. So anyways, we get a nice posterior probability density function here. It's fairly sharp given the data model that we have adopted. I didn't include any excess variance, so we may be under dispersed on the data. And we get a regression that goes through the data set like that. So just want to illustrate that this error in variables model is essentially choosing a point to be somewhere within its error ellipse. And that's pretty good model for a case where you are kind of viewing each of these points as being somewhere within that error cloud, and you want to know whether they hit somewhere along this line. So that works out pretty well. Intrinsic variance won't mess with you, bad data won't mess with you, but all of these things you can just plug in modularly and increase the parameter spaces as long as you have the time and to sample them. So I wanted to close out with a couple points about other fitting considerations that you may encounter as you go through your life. One of which is limits and censoring. This case is a measurement where you don't know exactly what the value is, but you know that it's on one side or other of a value. We often call this in physics, that's an upper limit or a lower limit. In statistics, you will find that this is referred to as censoring of the data. For some reason, you didn't observe a certain datum, though you have some constraints on it. And this often happens when you log scale data. So if you take a bunch of measurements and you do a logarithmic transform because you want to turn a power law relationship into a linear relationship for fitting, you'll discover that a number that's like -2 plus or -5 in your original measurements will then log transform to a invalid number that your fitting does not want to deal with. And so you often will treat this as it's a lower limit. It's just below some particular value. The recommendation in those cases is just model the data directly. Operate in the linear space, have that measurement show up as -2 plus or -5 in your data, and go ahead and include it. That's real consideration there. But sometimes you just are missing a datum. Like, consider a thermometer that's taking measurements with a precision of 1/10 of a Kelvin. But the thermometer has some limit to it. So some minimum temperature, say 120 Kelvin, below which it just says, I don't know, it's cold, it's some value, but it's cold. In this case, what you could kind of consider is a probability model for the temperature that's essentially flat from 0 to the minimum temperature, and then it rolls off like a Gaussian above that threshold with a precision. So it's going to be somewhere below 120 Kelvin, but if it's at 119 or 120.05, you may still measure it as a below the data, so that Gaussian rollover kind of takes over at that point there. So you can have this nice piecewise probability model so that if the fit expects this datum to be above 120 Kelvin, and it's not, that contributes to your goodness of fit. But if it's below, it actually provides no specific contribution. So this gives you a way of kind of describing the data. So just pick a reasonable model. Notice I picked a temperature model and I set the minimum temperature to be 0 in Kelvin. That's a reasonable physics prior, that there aren't temperatures below absolute 0. So you can set this, and you can even pick in your model if you thought that it was below 120 Kelvin, but probably above 77. Otherwise, all the nitrogen would have liquefied in the system. If you have a range, use your knowledge as to what that data should be. Those data should be. The other one to consider is what happens with nonlinear functions. This requires a lot of times direct integration. When we did this with a line, we took advantage of the fact that when I slice through this Gaussian probability cloud, I get a one-dimensional Gaussian that I can use some transforms to figure out what the sort of integrated probability along that line is. In this case, we have a curve that's going through my probability cloud, and I have to actually take into account it is not guaranteed to be a Gaussian or even unimodal, given how pathological your fit could be. A cubic that cuts in and out of this cloud could have two modes along it. In that case, you really do need to take into account the idea of what is your data model around this line? What is my data model for an individual point? And consider the product of those two probability density functions and integrate over that. So it gets quite complicated, but I want to stress throughout this whole thing, your kind of golden signal, your clarion call should always be, what are you asking of your data? Regression, as we've framed it so far, is built around the idea of asking, how does Y depend on X? And this works really well in experimental physics. We are looking for evidence of causation using a well-controlled X. I change this X parameter in my experimental setup. I see observation Y. So there's this clear framework of saying, well, this is what I did. This is how the experiment responded. I can really explore that. But sometimes people want to use the ideas of regression to ask, well, what is the relationship between Y and X? I don't actually have a clear control and response between those two things. How then do we describe that relationship? It's just trying to summarize, and we don't know what is the controlled or responding variable, or even if there is a third control variable that isn't even being studied, and we're just sort of exploring two response variables. So what you need to do then is think about what goes on the x-axis. Is this analysis symmetric? Is Y versus conditioned on X and X conditioned on Y supposed to give you the same results here? The results that we presented earlier with the error in variables do have some nice symmetric properties, but they are still built around the idea of, what is the relationship of Y on what is Y on X? Once we sort of start sampling uniformly an angle, it becomes a more symmetric problem. So you can actually use a lot of that to kind of that framework to do these sort of relationships investigations rather than understanding the dependence of Y on X, where X is clearly the controlled parameter. The last things to talk about are some other types of regression. There are a lot of opportunities for doing regression without building these full data models. The gold standard is to do and really think about every one of your data. Sometimes that's hard. And there's a whole zoo of robust fitting strategies that are kind of designed for incorporating bad data without having to really worry about which data are bad. A couple that show up here that are fairly popular is called random sample consensus, or RANSAC. And the way that works, this is taken straight from the sklearn documentation. Thanks, sklearn. And it shows a regression between these two data sets where you have a nice, perfectly well-behaved line of data and then some bad points out here. And if you just do an ordinary least squares fit, you go through your data and you go through the bad data, kind of as expected. But you can use this ransack, which picks subsets of the data and does a regression to them. And it's a little like a bootstrap where you're selecting subsets and you look at the multiple random selections of the data and you look at the consensus of the fit parameters to determine which one of the fit parameters, sets of fit parameters, give you the best results. So it or it gives you the most consistent results and which subsets agree most frequently. The Thiel-Sen regressor, I actually don't know how to pronounce this, but this regression essentially looks at every pair of points in the data set and looks at the slope. So 2 points define a line, looks at the slope and looks at the distributions of those slopes and looks at the median of that as the fit. So if you have more pairs of data that agree with one slope than the bad data slope, you'll get a regressor, and you can regression that lies and describes the data set. So these two robust regressors provide a quick and dirty way of fitting a line to data without having to worry about cleaning up your data set too much, and also not having to build a full data model. So again, gold standard is to go back and do mixture models, but this is an acceptable route forward here. Another kind of common approach here is to use what are called softer loss functions in studying the regressions. So a loss function is essentially chi-squared, or chi-squared is an example of a loss function. And it's a function of this deviation. I'll use the delta variable because that's kind of what we did before, which is essentially a function y minus the data y minus the function of a parameter vector and a data vector x. So it's basically the residual absolute value normalized by the noise in that. So chi-squared is the least squared regression is the deviation squared divided by 2 is the parameter in the loss. And so the log likelihood wants to minimize the sum of losses. So G is some loss function here. And so chi-squared is quadratic, and therefore a point that is far from the line shows up as quadratically bad. So it really contributes horribly to the data set. A much more common thing that sort of treats all data equally is called the L1, which is referring to the L1 metric in kind of real analysis, which is just the absolute value of the deviation. So that is a nice approach, and everything kind of contributes linearly, and you don't have one bad data throwing off when there's a bunch of data that agree well with the line. Gives you a good result from that. Problem with the L1 is that it is, you'll often see this called absolute deviation regression here, where you're trying to minimize the you're trying to find the least absolute deviation. Least absolute deviation is unstable numerically, which is why we don't like it. It's not, absolute value function isn't differentiable at 0. And as a result, this can have a lot of numerical issues when you're trying to use minimization algorithms. A compromise, therefore, is to use what's called the soft L1 metric, which is essentially chi-squared out to 1. In the deviation, and then the L1 metric for everything beyond 1. So it's sort of, parabola at the bottom and then an absolute value function outside of that unit interval. And that's nice because the stuff near the line contributes like chi-squared, and things far away don't pull the fit off too much. Gives you some tools. Anytime you see, oh, this is a different loss function, that's usually the language that's used in numerics. What they're doing is they're messing around and doing some funky mapping of this deviation so that your things far from the line don't contribute or don't pull your fit excessively. But again, I stress that the gold standard is to do this full data model and to be able to integrate over all of these nuisance parameters to determine your final set. So we are in this acute need for an ability to kind of map out and integrate over high dimensional probability spaces. If we could do that, we would be able to throw in lots and lots of free parameters that we can integrate over as nuisance parameters in our regression. And that would allow us to build really rich data models. But unfortunately, we really can't do that with this grid tabulation approach. We grow quickly beyond what we can do there. And what we need to approach then is this idea of Markov chain Monte Carlo. Which is the thing that allows us to sample these spaces, integrate over parameters that we don't care about, and really tackle these kind of high-dimensional Bayesian analysis problems. So that's what we'll do next.